my YouTube channel all about VLSI. In this particular video, we are going to refer to the architecture which we are going to design. So basically, we are going to design an Ethernet MAC controller, and this is what we are going to design. So if you carefully observe over here in this particular architecture, we are going to have our CPU or the processor, and from this processor, we are going to have the Ethernet controller. This is what we are going to design, right? And this Ethernet controller to be operated by the processor, we are going to use something known as AXI interconnect. Using this AXI protocol only, we are going to control our Ethernet controller from this processor. So that's the reason this Ethernet controller is also going to have the AXI wrapper. AXI wrapper is nothing but it is going to have the AXI related signals. It's a top model where in the top model we are going to instantiate our Ethernet controller. And on the right hand side, you can see we have an Ethernet physical which is present. Basically, this is what it is going to convert whatever the digital signals into analog signals. And this is not we are not going to implement this. This is an actual IC which we are going to have on the whatever the board evaluation board which you are going to have, right? And if you want to connect this Ethernet physical IC with your Ethernet, whatever the Ethernet controller which was wrapped inside your AXI wrapper, we are going to use some set of signals which is known as MII signals, media dependent. Media independent interface, right? So regarding this MII interface, we have discussed in our previous sessions. If you haven't watched those particular sessions, I recommend you to rewatch them, right? So where we are going to basically use this particular MII signals for connecting this AXF wrapper with this Ethernet physical, and from this Ethernet physical, we are going to connect it with our external RJ45 Ethernet connector. And this is all we are going to have it practically, right? We are going to design this Ethernet controller and which is going to receive the frames from our processor and it is going to push them into our Ethernet physical. And also this Ethernet controller is going to receive the frames from this Ethernet physical and it is going to give it to our processor, right? Now, again, further, this Ethernet controller is going to have different sub-modules where like we are going to have something known as a top level module and TX data path, which is going to have the main functionality of this TX data path is to create the frame like a preamble padding. It is going to perform padding. It is going to perform frame check sequence, interframe gap, and it is CSM and CD. This is not, we are not going to implement it, right? And it is also going to have something known as RX data path. So this is for transmitter side. This Ethernet controller is going to have TX data path and RX data path for receiver side. And this is going to have it is also going to receive the frame Ethernet frame, and it is going to remove this particular preamble, and it is also going to perform frame check sequence, and it is going to filter it, right? And VLAN we are not going to implement in this particular series, and also it is going to have MII physical interface for basically controlling this particular signals. We are going to implement another module which is going to take care of this particular MII signals, and GMII and RGMI and SGMI we are not going to implement it. We will see in further future sessions we will implement them. And next we are going to have MDIO management module, and DMA also we are going to see, and utility and CDC and CRC, this and all we are not going to implement it, right? So up to DMA also, let's see if time permits, we are going to implement it. Now further moving, so how the data is going to flow, like I have explained you previously also. So the host SoC deposits the frames into TX FIFO. So whatever the processor which we have over here, right? So that will be pushing the frames into a FIFO. We are going to have a FIFO model, and the frames will be stored inside this FIFO. And the TX data path which I have shown you, right? That will be fetching the data frames from this FIFO. So the processor using this AXI interface, it is going to push the frames into the FIFO, and from this FIFO, we are going to the TX data path will be pulling the frames from this particular FIFO, right? And we are the AXI4 interface and the TX MAC controller. So we are going to have a module internally which is present, which is nothing but TX MAC controller, which is going to pull the bytes from the FIFO. So the processor is going to send the frames in bytes. It is going to store the frames in terms of bytes, and we are going to pull them, right? And the sequences stem through preamble and SFD generation, and it is going to make sure that it is going to have minimum length. So what do you mean by minimum length and all? We are going to discuss. and it is going to perform CRC, and it is also going to enforce IFG. What do you mean by IFG? What do you mean by CRC? We have discussed. IFG we are going to discuss in future, right? And the resultant byte is basically serialized into 4-bit nibble by the MIA interface model and driven into the MIA pins at the physical clock. Okay, so using this MIA, we are going to basically this TX is going to pull the data from this FIFO, and it is going to make a packet. And after making a packet, it is going to again slice it, and it is going to convert them into 4-bit, right? And it is going to give it to this MIA interface. Why 4-bit? You might have listened to the previous lectures where we have discussed about MIA interface. You might have known it, right? And after that, what we are going to do is we are looking into this receive direction. So MIA interface model samples 4-bit nibbles from the physical interface. So we have another model which is known as RX, which is going to receive the data frames from the semi interface. In the 4-bit, it is going to receive the frames in 4 at 4-bit rate. That is, it is going to receive the 4-bit nibbles from the physical on RX clock edge and reassembles into bytes. So after receiving 4-bit nibbles, it is going to reassemble into bytes. Okay. And we have a model which is known as RX MAC controller, which is going to sequence this particular bytes through preamble, FCS, residue checking, and all. And then it is going to give it to our AXI interface. If I want to give you an overall idea, this is what it is going to happen. In the TX side, the processor is going to send the data to the FIFO. From the FIFO, TX MAC controller, it is going to receive, pull it, and it is going to create a frame, and it is going to give 4-bit data to our MIA interface, and MIA interface it is going to send through the to the internet physical and to the external world, right? And in the RX frame, RX Mac controller, it is going to receive the data, 4-bit data from this MIA interface, and it is going to go through all the particular processes, and it is going to create a 8-bit frame, and it is going to give it to our processor. This is what the overall thing it is going to happen. And in detail, we will see like which clock this particular process is having, and on which clock processor is working, and on which clock this particular Ethernet transmitter is going to work and all, and which clock Ethernet physical is working. This is also very, very important things to be discussed, right? Yeah, this is what I was saying about. So TX clock is having 25 megahertz, whereas RX clock is going to have 25 megahertz, whereas AXI clock that my processor is going to working will be around 100 to 200 megahertz. And TX clock, where TX underscore TX Mac controller, whatever the model which I've told you, right, which is pulling the data from the FIFO, is going to use a clock which is basically derived from PLL, and RX clock is basically recovered from physical. So what do you mean by recovering from physical also we are going to discuss. And AXA clock is basically getting it from the SoC fabric itself, right? And yeah, this is a detailed description of each and every model which we are going to have in our Ethernet MAC controller. First, let us see about what are all the models which we are going to have in this Ethernet MAC controller in the transmitter side. And let's move forward and we will discuss about receiver side. So in the transmitter side, the very first model which we are going to have is TX MAC controller. This is used to control the transmitter frame, and this basically it is going to control whatever the sequences which we are going to have, and it is going to perform this operations which is preamble, SFT, and it is going to perform padding, frame check sequence, and interframe grab, and it is going to control the TX enable and TX error assertion on the MI interface. So this is the top model which is going to control all these particular models, right? And after that, we are going to have another model. This is the second model which we are going to develop, which is TX preamble. So what do you mean by preamble and all we have discussed when we are discussing about Ethernet frame format? If you haven't watched those particular videos, I recommend you to once go through it. And next is padding. So this is a third model which we are going to have, which is TX padding. Basically, it enforces 64-byte minimum Ethernet frame. So let's say if the Ethernet frame is not 64-byte, it is going to add padding, and it is going to track a running byte count over the payload, and it inserts zero value bytes until the payload plus padding reaches 60 bytes, right? And we are going to make it 60 bytes because we are going to also add frame check sequence to the final 4 bytes, right? Basically FCS is 4 bytes. We are going to add 4 bytes to the final frame, right? So this particular module is going to add the padding, and we are going to discuss in detail when we are going to have this module discussion, right? I'm just giving you an overview of what are the modules we are going to have and what is the functionality of each and every. And next is TX underscore FCS. This we have already discussed. We have also seen the coding part of this frame check sequence, how it is going to perform the frame check sequence. And next is TX flow control. This is the fifth model which we are going to have, which basically controls the pausing frames and all. We will discuss like what is this and what is it exact behavior and all. And next is TX FIFO. I've shown you, right? So from the processor, we are going to send the frames to our Ethernet MAC controller via the AXI interface, and it will be stored inside our FIFO, right? About this TX underscore FIFO also we will discuss. And this what we are going to develop is an asynchronous FIFO, and exactly how it is going to work and all, I will let you know, right? So these are the transmitter side modules which we are going to use, and we are going to discuss in detail like how exactly these modules are going to work and how the data is being flowing between these modules and how the data is being sent to the actual physical, right? Yes, so that's about this particular session. If you like this video, please like, share and subscribe to my YouTube channel all about VLSI. Thank you for watching this video.